Hello, today we'll be starting our study of rotational motion. Rotational motion is when an object or group of objects rotates about an axis. This motion is different from the motion we studied prior. Previously, we looked at when objects move from one position to another. This is called translational motion. Sir Isaac Newton formulated the laws that govern how translational motion is created and altered. Newton stated that an object in state of motion, meaning having a velocity, would continue in that state of motion. In addition, the only way the object could change the state of motion was to have a net external force acting on the object. That net external force would cause the object to accelerate or change its velocity in a given time. This change would result in the object going faster, slower, or move in another direction. If the sum of all the forces acting on the object resulted in zero net external force, then the object would not change its velocity, and the object would be in equilibrium. We will now refer to this type of equilibrium as translational equilibrium. Now, the question is, how do Newton's laws pertain to an object that is rotating? To begin our discussion, we need to set some boundaries. The world is a very complicated place, and understanding simplified versions of concepts will allow us a deeper understanding of the basic rules of rotation. Simplification number 1. The object that will be rotating will be rigid, meaning not allowed to change shape or density. Simplification number 2, we will start by looking at objects that are in static rotational equilibrium, meaning these objects are not rotating, nor will they. They are at rest. Now, on to rotation. Let us start with how forces acting on a rigid object affect that object. If you take a simple shape like a rectangle, and you apply a force to it, then the rectangle would change its motion. However, it depends on where on the object you apply the force. Apply the force toward the middle, and the object simply moves sideways, or translates sideways. Apply the force just above the middle, and the object slides sideways and rotates. Apply the force at the end of the rectangle, and the object slides with less translational motion and rotates more. How about a more complicated shape? Let's say we put two rectangles that are locked together and make an L-shaped object. What will occur when the compound object is struck and a force is applied? Well, that depends on where it is struck. If the force is applied to the top of the L shape, then we get a great deal of counterclockwise rotation. However, if we apply the force at the base of the L shape, then we get clockwise rotation. Where should the force be applied to get no rotation? For a rectangle, that is in the middle. But for the L shape, the middle won't work. That point of the application still causes rotation. This problem brings us to two new concepts: the concepts of mass distribution and center of mass. The L shape actually has more mass located toward the bottom of the shape, while the rectangle has more mass evenly distributed. If we imagine the two shapes as a single point of mass, then the rectangle's point would be located in its geometric center. However, the L-shaped mass would be located closer to the base, as that is where more mass is located. This point is called the center of mass. We will be looking at how to find and calculate the center of mass in a later lesson. Key concept is that if a force is applied to a rigid body at any location other than the center of mass, then translational and rotational motion will be generated. However, a force applied at the center of mass will only generate translational motion, no rotation. There's the first lesson on rotational motion, that forces generate not only translational motion, but they can generate rotational motion depending upon where the force is applied.